Hello everyone, today we will introduce CXL 2.0-based end-to-end system for high-performance memory disaggregation. Before moving on to the main talk, I'll give you a high-level summary of the talk. Our work's main research target is memory disaggregation, which can satisfy large memory requirements of various big data applications. Existing memory disaggregation use RDMA, but RDMA requires high monetary costs for specialized network interface card and switch, and it also degrades application performance because of microsecond level of memory access latency. Instead of RDMA, we suggest to use CXL for memory disaggregation. CXL can reduce monetary costs for memory disaggregation and minimize the performance degradation. However, CXL-enabled system is not available for now. In this work, we designed the CXL-based memory disaggregation, Direct CXL. Direct CXL implements CXL-enabled host, CXL memory device, and CXL switch. We also modified Linux kernel to expose CXL-attached memory to the user level application. Our evaluation using real hardware prototype shows 3 times better performance than RDMA-based memory disaggregation. Now, I'll explain what the CXL is and how CXL can be used for memory disaggregation. Compute Express Link, or CXL, is an open industry standard for cache current interconnect based on PCIe Express. CXL allows device to cache data stored in host memory without breaking cache coherence. This kind of device is defined as type 1 in CXL, and coprocessor can be an example of type 1 device. CXL also allows host to cache data stored in device memory, and such device is called type 3. Type 2 device mixes type 1 and type 3, and an accelerator with internal memory like GPU can be an example of type 2 device. Like this, CXL supports various types of device ranging from accelerators to memory. In this work, we focus on CXL.MEM protocol with type 3 device for the memory expansion, which allows host to access memory with load store instruction. From now on, I will show benefits of CXL-based memory disaggregation compared to RDMA in both hardware and software viewpoint. From the hardware viewpoint, RDMA requires network connections such as InfiniBand, so we need network interface card with RDMA support called RNIC. In contrast, CXL enables direct access to the remote memory, but we need CXL-enabled CPU and CXL controller for the device. We compare the single cache line load latency of RDMA and direct CXL. Let's see the RDMA case first. The data is stored in remote DRAM, so CPU will read the data and completes DMA request of RNIC. RNIC will send data through the network, and another RNIC at the host site writes received data to the local DRAM using DMA. For the CXL case, it only accesses remote memory when cache miss occurs. The data stored in remote memory is loaded to the CXL controller, and the controller sends data to the host CPU. As a load store instruction can be directly handled by CXL device, direct CXL is about 8 times faster than RDMA. From the software viewpoint, RDMA requires additional software intervention. When application calls RDMA function, user-level RDMA libraries must be involved to control the RNIC. In contrast, CXL does not introduce any software overhead as it accesses remote memory using load store instruction. As a result, the performance benefit is increased to about 24 times. In this section, I'll explain how we designed direct CXL by answering design questions. First design question is how CPU can directly access remote memory. Second design question is how to realize memory disaggregation using CXL. And last design question is how application can use CXL-attached remote memory. Let's begin with the first question. To enable CPU to access remote memory, the load store instruction issued by the CPU is directly converted to CXL packet. We prototype CXL CPU on a high-performance accelerator card and CXL memory device on a customized FPGA board. When application running on the CXL CPU issues memory request, the CPU will convert the memory request into CXL packet called CXL fleet. When the CXL fleet arrives in the CXL memory device, it converts CXL fleet back to the memory request and serves using underlying DRAM. The CXL CPU implements CXL loop port, which extends PCIe loop port with CXL support. In case of cache miss, CXL loop port will convert memory request into CXL fleet. The CXL memory device implements CXL endpoint, which extends PCIe endpoint with CXL support. It converts incoming CXL fleet into memory request so that the memory controller can understand the memory request. To realize memory disaggregation, direct CXL implements the configurable switch, which supports multiple CXL CPUs and CXL memory devices. Our CXL switch uses the same hardware platform with CXL CPU, and it supports 4 CXL CPUs and 4 CXL memory devices. The CXL switch includes reconfigurable crossbar, so the connection among CXL CPUs and CXL memory devices can be changed. User can configure the crossbar through Fabric Manager. After the configuration, the crossbar will connect CXL memory devices and CXL CPU, and the connection can be changed on runtime using hot plug and hot remove feature. To expose CXL attached memory space to user, we leverage Linux memory management system. Software runtime of direct CXL is consist of enumeration phase, initialization phase, and usage phase. When Linux PCI bus driver performs enumeration, our CXL host bridge driver discovers CXL memory devices. Remote memory of each CXL memory device is mapped to the system so that the CPU can issue memory requests to the remote memory. Our CXL memory device driver is loaded after enumeration, and the driver exposes character device to interact with user-level application. User can create namespace through IOCTL, and user can perform mmap on the namespace device to use the CXL attached memory space. mmap handler of CXL device driver will map physical address space with remote memory into the user's virtual memory address space. So the user can issue load store instruction to mmap memory to use CXL attached remote memory. Finally, we will show 2 demo videos. In the first demo, we will compare the performance of recommendation system using existing RDMA-based solution and direct CXL. We use DRM model for meta, and the whole embedding table is stored in the remote memory. On the left side, there are 4 customized FPGA boards for CXL memory devices. On the upper right side, 4 accelerator cards are used for CXL hosts and 1 for CXL switch. Each terminal shows the booting process of each host. Each host's local memory is 1 GB, and I reserve additional NUMA node for remote memory. Our direct CXL driver will communicate with Fabric Manager to attach or detach memory devices. For the comparison, we use same accelerator cards for the RDMA system. We use InfiniBand FDR for RDMA network and 1 NVMe SSD for creating swap partition. Each node has 48 GB of system memory, and the InfiniBand is initialized correctly. We ran our DRM workload and compare the execution time of each step. In the tensor initialization phase, we filled the embedding table with random values. In the inference phase, we performed 10 inferences. Direct CXL was 2.8 times faster than RDMA in inference phase and 3.3 times faster in end-to-end. In the second demo, I will show how CXL switch can be used for memory disaggregation. On each host, 4 CXL memory devices are available to use, and each host has 900 megabytes of system memory. I'll attach one CXL memory device per each host. After attached, the system memory is increased to 17 gigabytes, and the 16 gigabyte of remote memory is visible in NUMA node 1. Assume that the host A requires more memory. I'll detach the memory of host C and D and attach them to the host A. After detached, the system memory is decreased to 900 megabytes. After attached, the system memory is increased to 49 gigabytes, and the 48 gigabyte of remote memory is visible in NUMA node 1. In this work, we showed Direct CXL, the world's first real CXL version 2 system for memory disaggregation. It supports CXL from bottom to top, including hardware and software runtimes. Also, it reduces monetary cost of directly accessing remote memory, and it achieves high-performance remote memory access.